Greetings and welcome to another video. So what I've been doing a lot of in recent videos is taking a cap and discharging it into another. So maybe 3 or 4 videos ago we discharged a cap through a coil, and then we saw when you put a conducting diode in series with the coil that you could transform voltage upwards. And then we took a cap and just discharged it through a coil, put the same conducting diode there, and saw that when you had the thing at the right frequency, it would really transform voltage, and that was the boost circuit. And then in the most recent video, took a cap, discharged it through a coil, and we noticed what would show up in this cap when we discharged this cap through a coil of wire. And then when we put this one diode in here, that's in a blocking configuration from the positive to the negative of the cap that you're discharging, you got more voltage out in both caps than if you just, so you can just discharge this cap one into another. If you're at 10 volts, then this is about 1/100th the size. They both end at around 0.1 volts. Now you discharge the cap through the coil, and you put this one funky diode in there, and they both end up at 0.35 or 0.4 volts. You get 3.5 or 4 times more charge. It's violating Ben Franklin's conservation of charge. Sorry, Ben. And then what occurred to me over time was that that happens every single time you have an electromagnetic step-down transformation of voltage, going from a higher voltage to a lower voltage. If you ever want to go from a higher voltage to a lower voltage, you might as well use a transformer or something like that, because you get a lot more charge out. What we're going to do now is, with this blocking diode here, it's starting to look now a little bit like something called the buck boost circuit. So we'll look at the buck boost circuit and what it is, and then we'll set it up and run it with the Arduino. And I want to kind of do a little bit of a deep dive on this, because there are things that I understand with it, and there's still some stuff that I don't understand. And you know, I've been thinking about it when I go to sleep, and I can't figure it out. But I realized, hey, I picked up an oscilloscope. So we'll put it on the oscilloscope, and I'll see if I can figure out exactly what's going on. I'll show you what it is that's confusing me once we get the circuit up and running. So we're going to build a buck boost, and then we're just going to examine it in detail. Okay. So here's the Wikipedia right up on the buck boost. So there's the buck, there's the boost. We built that one already. Now here's the buck boost. They're not real clear here, but this would be a power source, and this would be your positive and your negative. And so you can see that the diode's in a blocking configuration against the positive, and there's your inductor. And it's just where you place the diode, whether you call it a buck boost or a buck. Or if you like, we can go to, which I think is a little more clear, this engineering company website, and here's the buck boost again. See, there's your power supply, a switch, a blocking diode going out to the capacitor, and there's your inductor. Now, since the diode is in the backwards configuration, it's what's called an inverting transformer. In other words, with this being positive, this will be the negative on the cap, and the positive of the cap is connected to the negative of your power supply. So where have we seen something like that before? People who may have played around with the Bedini stuff, there's all kinds of different circuits. Let's, I think this one, I don't know who put this one together. This might be Rick Friedrich or whatever, but here's one for the Bedini. And what do we see? We see the positive of the power supply going through a blocking diode to an inductor, and the negative of the power supply connected to the positive. Go back to the buck boost. We see the positive of the power supply connected to a backwards diode. The negative, if this you call the capacitor your charge battery, the positive rather, connected to the negative. So where were we? This part here is a buck boost, and then you just have the timing switch, and while you're doing the buck boost conversion, you're also spinning the rotor, which is really cool. But instead of doing that today, let's just build the buck boost part on the Arduino. You have to say it Arduino, or the purists get upset at you. I like to say Arduino, like Beano, but you're not supposed to do that. So the main difference that we're going to have here is that we can see in this circuit it is a constant DC power supply, and if you buy like a buck boost circuit off a DigiKey or something, that's what you're getting. And also here they have this as a constant power supply, it'll be constant voltage power supply. We're going to add one wrinkle in that we're going to have it as a cap. And so we'll charge this cap up through here, then we're going to do the buck boost thing, and then we're going to gather what comes out, that inverting voltage, out into another cap. And why am I doing that? It's just because I'm trying to understand exactly what's going on. And when you do it with the cap, there's the resonance of the cap and coil as an LC tank circuit, and that's the part that I'm really trying to figure out, and that we'll throw it together, and you'll see what I'm talking about. So let's build this in parts, and it's kind of how I would do it anyways, just to make sure things are working, and it should make it easier to follow along. So we have this one switch here. When that switch turns on, then this cap charges. And all I want to do, to start with, is just short this cap through a coil. So after that's charged, that switch shuts off. This switch turns on. The positive goes to there, across the switch, around the coil to the negative leg, and discharges the cap. So let's just see if that part is working. And there's no need to go crazy with the voltage, especially if you have something wired wrong. And so we see it charging up to 2 and discharging, and that's just like what we have for the code. Pin 5, that's letting the cap charge, then shut that off, and then pin 8, that's discharging the cap. So now we just need to do the buck boost part, and that's why that diode's there. So if we think back to our schematic there, the first thing we want is a blocking diode coming off of the positive of the power source. So I've got a backwards diode there, and I'm just going to put it in here. Because it's inverting, that positive leg is going to the negative of our gather cap, and then we need a line going from the positive of this cap out to the negative here. I've got this yellow thing sitting here. Why don't I just use that one? So now we have the buck boost set up. We got the negative connected to the positive. We got the positive going through a backwards diode to the negative. So let's first see if it does anything, and then let's have some fun with the timing. Okay, we have a buck boost converter. And so we got that diode there, that there. This cap fills up, shorts across the coil, and those connections are made to here. And I've gone up to 10 volts, and so we see it charges up to 10. Charges up to 10, and then it discharges to 0, and we see 0.323 volts showing up in the large cap. And then I also just re-put the code in there to short this cap once you're done, because once you start not having delays And, you know, with the for loop, even without the for loop, if you didn't have any delays and you don't discharge this thing, this is a transformer. So even at 5 volts, you can be up past 100 volts before you know it, and then kapoof. But I set it up this way to start with because if you remember from the last video, this is a 10 UF cap, this is a 1000 UF cap. When they connect, this was from the last video, when they connect in parallel, you have 10,000 UF, or rather 1,010 UF of capacitance. So if this starts at 10 and this is at 0, then they should equalize to just under 0.1 volts. But they both equalize to like 0.35. Now here, even though you're shorting the thing, we're seeing the same thing. That's too much charge. You know, that's more charge than you would get if you just discharge this thing into here. And here you're shorting it and just gathering the induction across the diode out to a cap. So now let's change this cap out for a smaller one, and let's run it faster and see what happens with transformation of voltage. And there's one thing I'll show you that it took me a while, but I do understand, and then I'll talk about the stuff that I don't understand. So here I just threw in another 10 UF cap. We're just doing the same thing. So it's, you know, charges up to 10 volts, and when it discharges, we see a little bit over 5 volts show up in here from the buck boost part. So first thing we'll do is we'll just run it faster and repeatedly and see how it transforms voltage. Now there's going to be a spot where it transforms voltage really well, and I'll show you what that is. But to determine that, one of the things is, what is the resonant frequency of this? And on one hand, you have this cap is discharging through a coil into here. And so you say, well, it's the 10 UF and the induction of the coil, and then you calculate it from there. And I think that's correct. However, for half of the oscillations, there is an electrical connection to this other 10 UF cap. So for that part, is it 20 UF? And I think, I mean, that's where the oscilloscope is going to come in handy to see what the waveform looks like. Is it just going to be a smooth sinusoid, or is it going to look a little bit different? Because for half of this, you know, this is not a blocking diode. It's a conducting diode. When this coil is flipping back and forth and the cap voltage is flipping back and forth, half of the time it's blocking, half of the time it's conducting. And you use that trick to trap higher and higher voltage into here. So let's first just run it, and I'm curious if it's not in resonance, if it transforms voltage at all. So we have a 10 UF cap. The induction of this coil is measured as about 91.3 millihenries. So if we go to our spreadsheet that we have together here, we got 91 millihenries, 10 UF. The resonant frequency is 1 over 2 pi times the square root of LC. Therefore, the time from wave crest to wave crest is 2 pi times the square root of LC. So for this, once we plug that number and that number in, and we just let it calculate for us, the resonant frequency is 166.6 hertz. The time from wave crest back to wave crest is 6 milliseconds. At 3 milliseconds is where this thing would go most negative, and at 1.5 milliseconds is where it should discharge to 0. So first, let's just put in 1.5 and 3 and see what registers on this. Well, before we even do that, let's just run the thing at like 40 milliseconds, so we know it's way out of resonance, and see whether it transforms voltage at all. And then I want to look at dish, and I'll tell you right now that this one should be the one where it really transforms voltage. This was the one where when I first saw that, it threw me for a loop, and then I had to think about it, and I'll show you that one. So the first thing I've done is I've just set the discharge time to 25 milliseconds. Now we said the wave crest to wave crest is 6 milliseconds. Where it gets interesting is down at like 1.5 and 3. So this is way too long, but does it do anything? So we're doing it 50 times fast. And we see we get some transformation of voltage, but it's pretty meh. You know, I mean, we're starting at 10 volts, and after 50 times we're at 12, 12, 13 volts. So that's not much of a transformer. But let's back up for a moment and go back to just doing the one pulse thing, because we want to figure out what is the resonant frequency here. And so if it's based off of 10 UF, then wave crest to wave crest, 6 milliseconds. At 1.5 milliseconds, you would have a quarter wavelength for this 166 hertz oscillation. At 3 milliseconds, you'd have a half wavelength. And so what that means is at 1.5, this cap should go from 10 down to 0, and at 3 milliseconds, it should go as negative as it's going to go if the oscillation is based off of 10 UF. So what I've done here is just set the on time equal to 1,501 microseconds, 1.5 milliseconds. And then where are we? I've gotten rid of that 25 millisecond delay. So we'll just discharge for on time. And what we should see here is this cap going from 10 to 0. And what we see is it goes from 10 to negative 0.68. So I'm fine with that. This could be 10.5 or 9.5. The induction might be a little off here. That's close enough for government work. So now we set the timing to 3002 microseconds, or 1/2 wavelength. And what do we see? We see the cap going from 10 down to negative 5.78, which it's interesting it's going negative, but we know from previous work with this that this is pretty high Q factor, and it should go 10, negative 8.5, negative 9 even. It's not, though, because of the load here. And so what we're going to do now is we're going to repeat this, just doing it one time each, and we're going to look also what's showing up in this cap each time. So we've gone back to 1501, or quarter wavelength, and now we're going to look at both caps. Ooh, scary, very scary. Joe Flaherty, Second City TV, Count Floyd. So this again is going from 10 and discharging to 0, and this cap is going up to 7.6. So recall I was saying that there's pretty high Q factor, and we should be seeing like 8.5. Now we are seeing that because you take the voltage drop there. These diodes, it's even more than 0.6. It's like 0.8. And we're just about, like 8.5. So really all we've done is we've shut the thing off, any connection to here, right when this coil is entirely full, and we've let, instead of it circling back down as it would with the LC tank oscillation, it now circles out to here. So that's what that's doing. So now we've set it to 3002 again. This is going from 10 down to negative 5.7, and this is going from 0 to 5.4. So it's not going back up to 7.5, but there is something showing up there, 5.4, and it's kind of interesting that we start off with a single cap with 10 volts in it, and now we have one with negative 5.7 and 5.4. So I mean, if you flip that cap over, then you again have a problem with too much charge being around. So this is actually not entirely unexpected either, because what you have, okay, when we got to quarter wavelength, all of the electrostatic charge on the capacitor is now in here as a magnetic field, and the capacitor is at 0. Then it collapses, half of it shuffles back to here, and because it's now a negative voltage, this is no longer a blocking diode, it's a conducting diode for that part of the cycle, and half of it shuffles out to there. That makes sense. Now, it doesn't fully make sense to me why we're getting, this is negative 5.7 and this at, I bumped a wire, let's see. Yeah, 5.4. So we're getting too much. I mean, it should be negative 5, or, negative 5.6 and negative 4.4. Yeah, I think that's, like Bedini talked about it as nodes. And I think that's what's going on there, is now you have two nodes. And so you get a little bit extra charge. So it's subtle, but it is there. And when I saw this, some time back now, I was thinking, well, all right, just put in some switches to flip the cap back and forth there, and, you're off to the races. But there's another thing that happens, which is not so good, and which I still don't, I'm not sure I understand. And so let's go back to the quarter wavelength. And we'll run it 50 times fast again, like we did when we had that delay of 25 milliseconds in. But now it's only going to delay for 1,500 microseconds. When we ran that before, we saw it went from like 10 to 12 or 13 volts. What we see now is it goes from 10 to 60 volts pretty darn quick. And so that's what it does there at the quarter wavelength. Now, if we go to the half wavelength, and we run it 50 times again, we see it's going to 8 volts. It's not even making it back to 10. I think that's just because this is a cheap meter, it's leaking out, and there's the voltage drop across the diode. So it wants to get back to 10, but it can't do it. So that place where this thing goes negative doesn't transform voltage. And I'm not really sure why. So again, back to 1501, and we're shooting up to nearly 60 volts after 50 iterations. 50 iterations at 3,000 microseconds, and we're not making it back to 10 volts. Now, the thing that has me confused is that 1,500 microseconds is shorter than 3,002 microseconds. 1,500 microseconds occurs first, and then 3,002 microseconds occurs. So there's obviously something really simple that I'm missing, but what I can't figure out is to get to 3,000, it had to go through the 1,500. At 1,500, it's transferring voltage like a champ into here, and you have a backwards diode. So how did that voltage get back out? Or how did it know not to go in because it was going to be coming up on 3,000 microseconds? So again, each time 1,500, there should be well, I don't know, maybe I do understand it. Let's just talk through this. So this thing discharges to 0, and now this is as full of magnetic field as it's going to get. If you cut it off there, all that magnetic field shoots out to here. If we wait, then this magnetic field drains out, and it drains out by shooting this negative and putting half of it out to here. It should still transform voltage, just half as quickly. So I know this isn't, like some quantum mechanical, like the double slit experiment with photons and interference patterns. It's not that it knows whether it's 1,500 or 3,000 microseconds. There's just something simple that I'm missing, and it kind of annoys me. But I would think that it would still transform voltage just half as quickly. So I'm sorry I don't have an answer to that. But what we'll do is, since I bought the oscilloscope, now I'm an expert. Then we'll put it on the oscilloscope and try and see if we can see it like draining out backwards through the diode each cycle. I mean, that doesn't make any sense. Again, I got nothing. I got absolutely nothing. But what I will say, and and why it kind of bothers me that I don't understand this, is that with the Thane-Heinz bitoroidal setup, that is where you can take this cap and discharge it, and it won't go to -5. It'll be wanting to get back to -7, even -8, and you'll get transformation of voltage. And that's why that setup is so cool. And we're going to go back to that in probably the next video. I think I've done about as much as I can with this. But that's where you kind of divorce the two, the Lenz law effect back on the discharge of the coil from just the discharge of the coil and the Q factor that's happening there. That starts to get divorced some. Thane speaks of it as a magnetic diode. The other analogy that I think would be appropriate is it's sort of like the two-stage oscillator of Velko-Malkovich, which is, you know, a mechanical. Maybe we'll build one of those, 3D print one, but I think it's really analogous to that, the bitoroidal transformer is. But let's just put this on an oscilloscope and see what we see and wrap this up. Get it. I get it. I'm so happy. I'm sorry. I don't mean to like perseverate on this. It's just, you know, I'm going to go back to some of the stranger stuff with the bitoroidal. And it's like, if I don't even understand discharging one cap into another, how am I supposed to understand that? I get it. It of course, it was so obvious. So let's wrap things up here. This was fun. I'm just kidding. So this is at 10 volts, and you discharge it the first time, and this is at 5. And then, you know, this starts to get to 10. So now this is at 10 volts. It can discharge in short, or it can go into this cap, which has 10 volts. So yeah, I mean, there's a connection there. It could go in there. But this is already at 10 volts, where if it goes here, it can just discharge. So, you know, it's like the Yogi Berra thing. You know, nobody goes there anymore. It's too crowded. So once this gets up to nearly equal with this, then nothing more is going to go here. So that's why you have to break the connection when it's at 0, and then you get the transformation of voltage. So the oscilloscope was useful. So here it is at 3002. This is where it doesn't transform voltage. And we're going to do it 5 times. And I've just kind of frozen this. So the yellow is this cap, and the purple is this cap. So this here is where that cap charges up, and then it discharges. Now, the first time, you know, it discharges, another sort of interesting thing to see is it discharges. Wait a minute. I got this kind of backwards. It knows the voltage is negative. So the further down the purple line is going is the more negative voltage that you're getting because it's inverting. So it charges up, and then it discharges. And then here is where it's at 0. Now it's discharging, and they're both going one into one cap, one into the other cap. Cap charges up again, gets to here. It gets to, you know, halfway discharged, and now the negative voltage is coming from the coil collapsing, and it has to decide, well, do I go into this one, which already is at, you know, like -5 now, or do I go into this one, which is, you know, at 0? And so we can see this goes down further, and then it goes down even further. And then eventually you have where, you know, this one is nearly at -10. And so essentially nothing goes into it because, you know, it's saying, do I go into the one with -10, or do I go into this one, which is at 0, and push it towards -10? So that's why it does that. Let's just look at it where it transforms voltage. So here are those 2 traces. I can't believe this thing's actually really useful. So here's this cap charging up to 10 volts. Then it discharges. Now, previously we would have seen them both going negative like we saw, you know, in the previous one. But now we've cut off the connection to there. And so that goes out to there. and then the cap charges up again. Discharges. Now it's cut off. Then a short, few microseconds later, the coil is discharging, pushing this further negative. Boom, further negative, further negative. And let's do it like 20 times. I'd have to diddle around with all the different axes, but you can see that it's just continuing to transform voltage. So I'm glad that I finally, I don't mean to sound so pleased, but that was bothering me, and I'm glad I understand it now. Of course it doesn't go in there. It's too crowded. Okay, so that's it for today. Thanks for coming along if you made it this far. And stay healthy. Yeah, I think we'll go back to the bitoroidal transformer in the next video. Ciao. Take care.